see you. When did you come in? How long have you been here? Well, anyway, it doesn't matter. Would you care for some wine? Like to hear a story, maybe? I know one story in particular you might want to hear. Yeah, the year was 1997. Love was in the air. What a year. It's a story of compassion, anger, and M5 Branes. Come, sit for a while, and we'll go on a journey through time and space.
As most of you probably know, M theory contains two fundamental objects. M2 branes, which are three-dimensional, and M5 branes, which are six-dimensional. Our story concerns the latter. Throughout this, we're going to be working in a low energy approximation for the branes, which is the same as sending the Planck mass to infinity. Let's start by placing our brane at x capital I is 0 in the space-time. We can then perturb the brane away from xi equals 0. This is going to give our theory scalar fields, as we can define the pullback of these coordinates onto the brane to be scalar fields capital Xi. It's not hard to show that these scalars will propagate along the brane following a free massless wave equation. Counting the directions transverse to the brane, we see we have 5 of these scalars. Our fermionic degrees of freedom come from a Higgs-like mechanism. We're going to break half of the overall supersymmetries in 11D Minkowski space, that's 32. The broken killing spinors become our world-sheet fermions, whilst the unbroken ones become our supersymmetry parameters. And the Dirac equation is going to further half this again to 8. I encourage you to check this yourself, but the degrees of freedom of a self-dual closed 3 form in 6D is exactly 3. It will make up our difference perfectly. So now that we have our field content, we've checked that the degrees of freedom on shell for fermionic and bosonic match, we would like to see how they act as a supersymmetry multiplet. Applying the Soucy generators to our fields, we can derive the transformations of the multiplet. The name 2, 0 is a reflection of the supersymmetry that we see. In D equals 6, we have n equals 2 supersymmetries, but only of one chirality. Looking at the transformation rule for H, we see that it is not actually self-dual. However, the difference of H and H star is proportional to size equation of motion. So on shell, H is self-dual, as size equation of motion vanishes on shell. Furthermore, we see that the algebra doesn't even close unless you impose the equations of motion. So if we commute 2 transformations on any of the fields, we'd expect this to be 0 up to symmetry transformations of that field. What we see instead is it is not 0 and there's a leftover part, and in fact you can actually use this leftover part to define the equations of motion. It's what needs to vanish for the algebra to close on shell. So since we know H's equation of motion is dH is 0, we can say that locally H is d of some 2 form, we'll call it dB here. Now the natural way that you would try and make a Lagrangian for such a term is to add something like star H wedge H. But since we also have that H is self-dual, this is just going to be identically 0. So that's enough setup. This is how we're going to proceed. We're going to take 2 zeros theory in 6D, and we're going to place it just on flat Minkowski space, but we're going to use light cone coordinates. We're going to then assume that x plus is periodic, and we're going to make that period very small, so we're going to reduce on x plus. Crucially, this is going to have the effect that dx plus is going to annihilate everything in our theory. As we will see, these constraints on the system will actually be enough to form a Lagrangian for the equations of motion, and it will be supersymmetric under the earlier tensor multiplet transformations. Recently, Neil's done some work in actually forming Lagrangians for them without using the tricks I'm going to use here, so you should definitely go and read his papers, but I won't mention them further now. In using light cone coordinates, we are creating a natural plus minus I divide to the components of H. We label these as shown F, G, F minus, and simply H. We can now see what self-duality and closure in 6D implies for these lower dimensional fields. It's important to remember what the metric is if we're using light cone coordinates. Using this 4D Hodge star, we can decompose the self-duality of H in 6D to give us 4 equations. The last 2 of which tell us that we can eliminate either F minus or H from the equations, and we're going to choose to eliminate H. The closure of H in 6D again gives us 4 equations, The first of which tells us that f is closed in a 4D sense. The second one is a complicated differential equation involving g and h. Again, we can eliminate h for f minus if we please. The equation here for f is much simpler than that for g because we've assumed a null isometry in the x plus direction. If we combine the first and third equations, we see also that we can define f to be a 5D object and closed in a 5D sense. And that told us that there exists a gauge field which sources f. Now here comes one of the key steps. Focusing just on f and g for now, we see we have 4 equations, 2 from self-duality and 2 from closure. We're going to define some of these equations to be equations of motion, and we're going to take others as identities. In particular, we see df equals 0 as a Bianchi condition, and g equals star g is simply an irrep of SO4. The other 2 equations we take to be equations of motion, and the next task is to find an action that reproduces them. Now it's important to bear in mind that the action we find will be for 4 plus 1D. We're not finding an action for the full 6D theory. I encourage you to pause the video and check if you like that this action does indeed reproduce the 2 mentioned equations as equations of motion. What's really nice here is that g is acting as a Lagrange multiplier for f, enforcing f's equation of motion to be anti-self-dual. But we didn't introduce g as a Lagrange multiplier, it's a part of h already. So in a sense, when reduced, h acts as its own Lagrange multiplier on another part of h. We can also chuck in the action standard for fermions and scalars. And also, for those not familiar, when you perform a null reduction, you end up with Euclidean space, same as if you compactified a time-like direction. So we found an action which represents the self-dual and closed nature of H. But we had to make a null reduction to do it.
But Tristan, what do you mean by null compactification?
That's an excellent question, Maxime, and I'm glad you asked it. Why don't you write your question down so we can better understand what it means? Thank you. He does raise a good point. It is very unphysical to take a compact null direction. Now, from here, there's 3 things that we can do with Maxime's excellent question. Firstly, we can put it under the rug with all of the other questions that make us feel uncomfortable as physicists. The second option, which was the option of choice in the 90s, is to take a space-like isometry, so a space-like compact direction, and try and rotate it to be a null direction. Now, if you just simply rotate it, because of the proper length having to be conserved, you're going to see that it's going to diverge as a direction. So the trick is to take a simultaneous Lorentz boost into an infinite momentum frame, and if you set things up just right, you can end up with a constant length once it's null. This is a dubious process. It has problems with orders of limits and various other things, but above all else, the length of the vector at all times remains 1. So you're not really taking a null compactification in the sense of a null killing vector. It does not exist in this space-time. The third option, which I won't discuss much here, is actually a very exciting prospect for future research. It's something Rishi, Neil and Paul from our group have been working on. It involves taking a conformal compactification, so we exploit the conformal symmetry of the theory to conformally pactify x plus into an interval. Now, this is not strictly the same thing as taking a compactification by imposing periodicity, because we don't impose periodicity. You've simply taken the infinite range of x plus coordinate and made it into a finite range, 0 to 2 pi r. We should definitely discuss this more after the video, as I'm sure they have a lot to say about it. The obvious thing to do after solving the theory for one brane is to stack many branes together, as string theory teaches us. This is going to give us a non-abelian generalization to our theory. The gauge group is going to be UN, and as is common for all supersymmetric gauge theories, all fields must be valued in the adjoint. Now, the work me and Neil did in a paper that came out earlier this year is to take this non-abelian theory and put it on as general background as possible, by which I mean as general a background that will still have some supersymmetry left over. In the same light cone coordinates as before, this is our new choice of metric. Later on, we'll include other supergravity-like background fields, but for now, let's just stick with the metric. One of the changes we have to make in going from a flat background to a generally curved background is that we have to modify the killing spinor equation to a conformal killing spinor equation. So beforehand we had d epsilon is 0, now we have to have d epsilon is proportional to some other spinor. We call it here eta. Again, we might also have to add new terms to the action that weren't present in the flat theory and also to the transformations. Now what you find when you do this is actually quite interesting. You find two very distinct types of solution. We call them in the paper case 1 and case 2. The structure of case 1 is extremely similar to the flat space case. Of course, all of our covariant derivatives are now curvature covariant as well as gauge covariant. We also see the addition of a curvature of the 4 manifold term. But one of the most interesting features is this shifted derivative nabla, and as we can discuss later, this actually makes contact with the conformal compactification method I mentioned earlier. And for completion, here are the supersymmetry transformations for case 1 as well. The specific constraints we find for case 2 are in a way stronger. We find that we can't actually have any curvature of our 4 manifold. It has to be Ricci flat, and so we lose our curvature term. However, we pick up a term that looks like a Yang-Mills field strength, as well as this interesting term, which is a mixed Chern-Simons term. Again, for completion, I'll just quickly flash up the transformations as well. Okay, so now that everyone is thoroughly asleep with those long formulae on the screen, let's talk about something a little bit more interesting. Returning to the flat space case for a moment, just to simplify things, I want to talk about what happens when you integrate out G. The equations of f being anti-self-dual or self-dual and closed are called the Bolognesi equations. You might be familiar with these from Euclidean 4D field theories, in which you Wick rotate 3+1 space to 4D Euclidean space, and you find solutions called instantons that live on this Euclidean 4 manifold. They're characterized by instanton number, which is the integral of f wedge f across the 4 manifold. Now what's interesting here is we don't have just a 4 manifold, we have a 4 spatial manifold, but we also have a manifold parameterized by time, and here that's played by the role x minus. Some of you may be wondering, well, why do we need to do a null reduction to do all of this? We could have just done a space-like reduction, get a 5D super Yang-Mills theory, and avoid all of the sort of problems with taking a null reduction. And this is actually quite an interesting point because, of course, you can do that. That theory had been known a lot longer than the null theory had been known. But you wouldn't get the reduction to instanton moduli space for free. You would have to say, oh, there exist solutions in which we can move to instanton moduli space. Really neatly, we can actually tie this in with a paper by Rishi and Neal last year, in which they developed this technique of taking a non-Lorentzian RG flow. So this amounts to rescaling all the fields in your theory by some parameter, and the parts of the action divide into 3. They either diverge, stay constant, or go to 0. Divergence of the action in the path integral can be interpreted as forcing you onto the classical equations of motion. And that's exactly what we see here. So if we take the action from, say, this paper, and we perform this rescaling of the fields, we can see that we will eventually get to our action that I showed earlier. The last thing I wanted to talk about is one of the applications of all this work. So it's what I've been working on recently, which is deriving 1-0 theories from these 2-0 actions. So the general process is we want to break half the supersymmetries, and there's a variety of ways we can do that, including geometric constructions, etc., etc. But one of the nice things about writing the actions this way is that we can just simply place a chirality condition for epsilon, our supersymmetry parameter, under one of the R symmetry directions, one of the off-brane directions. This is going to cause a natural split of our tensor multiplet into two 1-0 multiplets, a standard hypermultiplet and another 1-0 tensor multiplet. The cool thing about doing this is that now the hypermultiplet is actually largely discoupled from the gauge part of the action. And so we can place the fields of our 1-0 hypermultiplet into any representation of the gauge group now. So I've only been able to scratch the surface of what's going on in this area at the moment, but I hope you enjoyed the talk, I hope you enjoyed the story, and please, if you have any questions, I'd be happy to discuss them at the end.